Thank you everybody for joining us today in the BASIRA AI for Healthcare seminar. So our keynote speaker for today is Dr. Ehsan Adeli, who is joining us from Stanford University. Dr. Ehsan is an assistant professor at the Department of Psychiatry and Behavioral Sciences at Stanford University, and is also affiliated with the Department of Computer Science. He served as an area chair in MICAI, Middle, ICLR, AAAI, and CVPR 2022. He has organized several conferences such as ICDSC 2017 and workshops in conjunction with MICAI, CVPR, ICCV, NeurIPS, and more. So we have been organizing the Prime MICAI workshop over the past 5 years. So it's a great pleasure to have you today. He is also an associate editor of IEEE Journal of Biomedical Health and Informatics and Journal of Ambient Intelligence and Smart Environments. Today, Dr. Adeli will give us a talk on modeling confounders and bias in medical studies in the age of deep learning. So this sounds really exciting. Thank you for joining us today. And I'll leave it up for you now to start your talk.
Awesome, thank you. Thanks for the intro. I am sharing the screen and hopefully it's the right one, the full screen version.
Looking great.
Yes, thank you. Yeah, I'll be talking with you on the topic of modeling confounders and bias in medical studies in the age of deep learning, as it was mentioned in the introduction. But before I continue into the talk, I wanted to very briefly talk about my research and research interests in general. My research revolves around jointly analyzing motion and brain circuitry. To objectively quantify motion, I use automated machine learning and computer vision methods using video recordings. And for analyzing the central nervous system, I use structural and functional MRIs. I do hypothesize that relating video recorded motor signs to neural systems quantified by structural and resting state functional MRI will identify novel multifaceted markers for different brain-related and movement-related disorders. And that's why I'm mainly working in two labs, one in the computer science department, Stanford Regional Learning Lab, and one in the School of Medicine, the CNS lab, Computational Neuroimage and Neuroscience lab, and working on multiple projects at the intersection of the technical and medical applications. Today, I'm here to talk a little bit more about the medical applications, and therefore, let me introduce our lab here as well, the CNS Research Lab, in which we perform lots of data collection projects. We are partnering with multiple national data collection projects in neuropsychological and MRI data collection. We focus on developing machine learning models, unbiased, confounder-aware, interpretable machine learning models, and use them to obtain discoveries. This work in this lab is mainly managed by Dr. Paul, who has been a collaborator in all of these projects, as well as Dr. Zhao, that I would be the projects that I'll be presenting today are joint works between the three of us. Okay, back to our topic. So before moving forward, let me first define confounders. A confounder is a variable that influences both the outcome or output, and the exposure or the input in a study, causing spurious or distorted association when building a model. So when we want to build a model to predict the outcome from the inputs, if the confounders are not properly controlled for, we may obtain inconclusive results. Let me give you examples. For example, when we predict the diagnosis from the brain images, age can be a very important and potential confounder. We know that brain looks differently in different ages. It has different structure and potentially different functioning during the aging, during brain aging, and therefore we know that age has a direct effect on the brain image itself. And at the same time, our studies have shown that these diagnosis labels can also be very much influenced by age itself. So, for example, in this example, you see distribution of Alzheimer's disease patients with respect to their age buckets are different. Our lab studies the effects of HIV infection on the brain as well, and as you see, the age buckets for the HIV diagnosis is also different. So basically, if this variable age is having effect on both the input and the output, if we don't control for it, there's a chance that this model is learning something that we don't want it to learn. This could be very, very simply created by, like, for example, having a data set that data set is already itself biased by, for example, different age ranges for the two classes, for example, disease and control. If we have this effect in the input data, we are not sure what this model is actually learning. It may learn the effect of age instead of the effect of the actual disease. And that's why it's very, very important, especially for neuroscience studies, to model confounding effects very efficiently and take it very seriously. So this is not just age, other, let's say, demographic variables, or even other variables like treatment procedures, drug usage, disease comorbidities, and so on. These are all very important potential confounders. There are some traditional methods in this space. The medical field and the neuroscience field was very much careful about these confounding variables. The traditional methods were mainly based on more traditional statistical methods that I'm going to very briefly mention here. For example, data stratification was one of the very popular methods. What they do is they often stratify, they group the subjects, the population, the study population with respect to the confounding variable, for example, age. They create different age buckets, and then they build different models for each of these buckets. This is very simple. And this works very well when the population is large, or when we are building very simple models in between. But when we are building a deep learning model, we want to use as many data points as we can, instead of stratifying and building separate models for each of them on the smaller cohorts. The other method that is being used traditionally is data matching. And data matching means that we match the two classes, for example, class 0 and 1, with respect to the confounding variable. We say, for example, age. Let's match the two classes 0 and 1 based on their age to have the same age range or mean and standard deviation between the two classes. This again means we get rid of some of the data points. We have to throw some of the data points away because we want to build this model, which is not favorable for building deep learning models again. We want to use as many data points as we can. One of the other popular methods in this space is removing the confounding effects using statistical methods. To do this, this brain image, we often extract some measurements out of the image. For example, the brain volumetric, the measures volume of the brain regions, for example. Then what we do is we residualize the effect of the confounding variable. For example, we build a model, a linear model, that we can basically remove any effect that the age had on this measurement. How do we do that? This is often the case. For each of the features, for each single feature or measurement, we build a linear model, a GLM model, between the measurement and the confounder. And in this way, we basically model the effect of the confounder on that single measurement. And we know that this line is, for example, the effect of the confounder on the measurement. Now the new features will be the difference of the effect and the actual value of the feature or measurement. That's why we call it this like the residual, the visualization, as you can see here. So hopefully this new set of features does not have the effect from the confounder. So this is another very popular method. But again, when it comes to deep learning, and especially end-to-end learning, that is very much popular these days, it is not clear how we can model confounders, how we can remove their effects. So even further than that, let me clarify a point here, the difference between bias and confounders. You see these names interchangeably, maybe in different studies, but I wanted to make a quick clarification what we mean by bias and confounders in our studies. This is the diagram I explained, and if I simplify it this way, there are like the features, the input features from the image, there are labels that are the outputs, and then the confounding variables that these variables will be having direct effect between to both features and the labels. So confounders have an intrinsic dependency with the label and hence lead to erroneous conclusions. That's the definition of confounders. While bias is often a matter of like skewed data distribution, which is sometimes referred to as selection bias, data selection bias. So this skewed data distribution bias is inference from the measurement. So still, this is also very important to be taken care of, but it's a slightly different in nature than what we refer to as confounders in our studies. So the goal for our studies, our research is basically to remove, at least for the features that we learn, remove any effect that this bias or the confounding variable has on the learned features. And by removing that, we are removing this spurious association that is created between F and labels, right? Back to our end-to-end learning frameworks, and you probably know how we solve problems out of in an end-to-end fashion. We often have a feature extractor that an input, a brain image or X is given to it, which extracts some features for us. We used to be using like convolutional networks here. After that, there were like the ResNets. And then more recently, we're using transformer-based models that extract features for us. Whatever we want to put here, I'm putting a box so that you know it applies to every other like more recent architectures as well. And then out of the features, we do classification or prediction, and then we have the label as the output. The model learns to extract features F based on which it could predict labels Y. And I always have mentioned that what is important for us is the interpretation of the models. We always want to go back and see what was the effect on X that was able to be predicting and was able to predict Y. And then we have different methods for that, but here let's just focus on these saliency map generations, for example, GradCam method and so on. So with this end-to-end model, the question is how to account for confounders. We've done several studies for interpretation, for independent feature learning, as well as end-to-end optimization, published in multiple different papers in different venues. Every time I come back to this slide, I will pause for a second for a little bit. If there is any question, I would be happy to answer. I'm seeing some questions in the chat, so
do you want to take them directly, or I can read the first question maybe. So could you clarify the difference between stratification and data matching? So you
absolutely
that, but can you go over it again?
Yes. So stratification means grouping the data based on, for example, let's say age. You group the subjects based on different ages, right? And then for each of the groups, you basically train one separate model. You build a separate model to do the prediction. So you have, for example, if you have 5 groups here, you have 5 different models that predict 5 different outputs, right? And then, but what happens in data matching, it's you have the same data set, you just throw away some of the samples so that you can balance the 2 classes. You will build one single model. So you match the data sets, or you just group them based on their confounding variable, for example.
Great. Yeah, so I think that's clear. So the first one is based on clustering. The second one is matching the distribution. So you have similar ages, so you don't end up having, discrepancy in, for example, an age if it's a confounder. Second question, using these traditional methods, how do we know that we have removed the confounder effect? Like, how can we check that if we use these typical, stratification matching methods?
That's a good question. There are these methods do not guarantee removing all of the effects, but what we often do is these, like for example, the diagnosis that you create, and then the scores before that, like for example, the last layer of your network, you get some scores that we often do some sort of what we call post hoc analysis, we try to do correlation analysis of those scores and, for example, the confounding variables, and see if those scores that we learn are highly or significantly correlated with the confounders. If they are, it means that the confounders are actually, they haven't been removed, and what we are learning could be the effect of the confounder and not the disease itself. There are some ways of like checking these again in a post hoc way.
Okay, cool. So, so I guess there are lots. This is a big area of research, and it's still developing. Now, another question. I'll take two more questions, and then we can resume. So, is confusion bias the same as confounder in the literature? The confusion bias. So here,
that's yes. That's that could be taken. In the medical studies, that's correct. Yes, I've seen in studies that confusion bias is more in the fairness literature, not in the medical literature. Could be taken as the same concept. I believe there is some like slight differences, which I'm not quite sure or confident about like discussing those right now here, but I agree with you that it's almost the same concept in the fairness literature, while in the medical and neuroscience literature we often refer to those as confounders.
Thank you. Now the last one. What about multivariate analysis to remove confounders? The multivariate analysis, because you can take into account the age and other factors when you're modeling or predicting. Yeah. What about that approach?
Yes, so I will talk about that in one of the future, like one of the topics that we have here as the presentation. But yes, this linear model, you can learn a GLM, the generalized linear model, not only include one confounder, but have a list of confounders here. We're still building the same linear model, just that it's multiple variables.
Okay, thank you very much. Ehsan. So yeah, and thanks also for those who asked the questions. Okay, let's keep rolling.
Yes. Okay. So let me talk about the interpretation part first. It's not the focus of what I want to talk about today, but I'll try to go faster on this. We talked about this end-to-end learning and how we can make the interpretation out of it. What we've done was this image, I don't know, it should be a brain image. I don't know what happened here. But anyways, what we do is, in this work, what we tried to do was just create interpretation. Although we know that a model was built with a bias present in the study. Now, when we want to interpret, we want to see what is the effect of that bias, what was the effect, the real effect of the diagnosis. So in order to do that, what we did was we said, okay, the feature extractor extracts some features. Now, this is the score that I told you, which gives us the diagnosis at the end. Now let's build that GLM model that I told you, the linear model here based on the scores, the confounding variables, and this is the feature itself. So basically we look at the feature and create this model based on the weights on the beta coefficients. We will know if this feature was confounded or not, if it's significantly, say, correlated with the confounder. And then what we do is we put this mask in here with simple operations, and then what we do is adding this dummy layer based on the mask and create some partial backpropagation implementation. So when we do this layer-wise backpropagation for creating the interpretation of the model, this time now we have this dummy layer that we put it here, it masks some of the features. So the features that are confounded, they are masked out. And what we see as the image, that's basically the interpretation of only the effect of the diagnosis, not the confounder that is masked out. This is the simple explanation of what we did, but let's see some examples. I talked about this HIV diagnosis from MRIs before. As you can see, this is the data set that we had in the lab at the time we published this work. And as you can see, there is a significant difference between the two age groups. Instead of matching it, we built this model and looked at the saliency map and tried to interpret the effects. So the left part of this image shows the saliency maps when the raw data is being used without the dummy layer. But after we add the dummy layer, we see that some parts of the saliency map are basically removed. When we look at the differences, this is the differences between these two. So this part basically was the part that our interpretation algorithm found out that was were more confounded by age, because age was significantly different here. And in the literature, we already know that these ventricles are significantly affected by age. As people age, the size of ventricles changes visibly and drastically. So this means that at least the interpretation that we were making and the algorithm is giving us the correct interpretation as we expected that. We tried the same algorithm on a large study, adolescent brain cognitive development, ABCD study, which actually in 2019 we did have a challenge organized with this data set for neurocognitive prediction challenge, as you see here, ABCD NP. So this study has over 10,000 kids ages 9 and 10 recruited, and then they are followed up every year. Still an ongoing study, but we use the baseline images from this data set. Their ages were around 9, 10 years old. The goal for this study was to see what are the pre-adolescent sex differences in the brain. The age here is not is basically matched. That there's no effect like difference between the two groups. The socioeconomic status of the two groups are also almost the same. There's no significant difference, but there was one variable, especially in this age range, significantly different between boys and girls. The pubertal developmental scale, or PDS, which the scores, as you can see here, are very significantly different, and this is p-value is the p-value of the difference between the two, and as you can see, it's very small. This is a work we published in Neuroimages 2020, and based on the same algorithm that I showed you, this is the heat map that we got from the differences between boys and girls, from the algorithm that shows differences between boys and girls. We used our masking strategy, and the masked images turned out to be these images, confounder free effects. And when we compare these two, basically this is the major part that is different, which is mainly affected by the PDS score. So, and this was an interesting finding that we found that, for example, the differences between boys and girls in that age of pre-adolescence is derived by different regions in the brain, one particularly in the cerebrum region, but that is mainly the effect of the PDS, not the differences in the in their gender. So we always do further analysis on the study on the brain and create interpretation out of the results. We mapped these results into our template space, and these were the significantly different regions in the brain. And we looked at actually the volume of some of these regions, and we saw that yes, some of them are significantly in terms of p-value of correlation. They are significantly different between boys and girls. Some of the regions were not significantly different, while they, in terms of volume, but they were found by our algorithm, our deep learning algorithm, to be significantly different, which itself is interesting because they are not different in their volume. It could be some other factors that the algorithm was able to capture those. We only checked volume here based on the limited pre-processing tools that we have. We only can check those measurements that are possible to extract. So this was the first part, only creating an interpretation out of the work. I'm seeing there is one question. Yes, the question, Islam, do you want to?
It's okay, go ahead.
Yeah, the question was the partial backpropagation is due to utilizing the mask, and the answer is yes, because now we decompose the backpropagation based on the mask that we generated with significant tests, and then based on that we could mask out some of the back propagated values. Okay, I will continue to the second part. This is what I where I want to now go to the understanding the effects of the variables, the biases, and everything in the learning stage. Now we want to learn features that are bias-free, let's say. Okay, back to our end-to-end framework. Now what we do is this, that we build a model this time that we know that we wanted to learn to extract features based on which we can predict Y. Now we want that still to be in place, but do this while invariant to confounder C via an adversarial component CP. So we define a confounder prediction module here, CP, that predicts the confounder out of the features. This is an adversarial component, which I will be talking a little bit more in our paper published here in 2021. 2021, what we did was we mainly studied bias, the general bias, while having this classification model. This classification is a simple binary cross entropy classification loss as we use in all of our studies. What we proposed here was for the bias prediction part, instead of predicting the value of the bias, we proposed a loss function based on Pearson correlation. So this time instead of going like predicting the value of the loss value of the variable, we used correlation as the component and as the loss function. So what we wanted to do was to basically remove the correlation between the features and the bias variables. And in order to do that, this function was used adversarially in our loss function, which defined the objective function here. The mean max is very much, you're probably familiar with it. It's the same as all GAN formulations. And we have our classification loss minus the bias prediction loss. And therefore, this, when we optimize for this, what happens is the feature extractor will learn to extract features that predicts Y, but doesn't predict B, or the bias, or the confounder, if we call it confounder C. So this was the study we published in 2021. Our method guarantees, because of this correlation function, Pearson correlation, guarantees mean statistical independence between the learned features and the protected variables or the bias variables. And in the this conference paper, we call them the protected variables, how it is referred to in the fairness literature. For the theoretical analysis, I think it would be great if you want to, if you look at the paper. So to test it, what we did was, for instance, we tested it on simple gender classification based on face images. A model that predicts gender from face images may have different recognition capabilities for different races with uneven sizes of training samples. And that's why we thought the race variable could be very much of an important concern and a significant bias in all face-based like gender recognition algorithms. So this was the test that we did on a study. In this work, we proposed this learning, representation learning scheme that I explained to you, that learned features predictive of class label with minimal bias in any generic type of bias variables. So what we did was, given an input face image and race that is quantified by a variable called shade, the shade of the face, the skin. The goal is to classify the gender of the input image. Here we show the average face images for each shade category. The average saliency map of a trained classic VGG16 baseline method is shown here. The accuracies of classification per class are shown as you see in the numbers here. The model is first pre-trained on the large ImageNet data set and fine-tuned on a data set called Gender Shades Pilot Parliaments Benchmark, or GSPB. As you can see, the accuracy drops as we approach to shade 6. This may be due to the data set bias where the model was pre-trained on. Results on of our model, in this work it was called BRNet, with the same VGG16 backbone are shown here through a color-coded normalized saliency map, as you see in this image. The per class accuracy is also, as you see, are here. It's clear from the results. Most of the classes have higher accuracies, exact same backbones. Only the adversarial component is added to it. And as you can see, the saliency maps are more or less the same. So for different races, the model is basically looking at similar type of features instead of being focused on different cues and creating less accurate models. This last column shows the TSNE projection of the learned representation by each method. Our method learns a better representation space invariance to the bias variable shade. As you can see, the previous model has like all of the larger shades, like for example, grouped together. So there is a pattern between the points, while our method in the representation space, in the feature space, we see less of a pattern. So in this study, as you can see, shade was one variable, which was the bias or the confounder, while features while the label was to say if this is a male or a female person. We compared our results with some other methods. Our method was obtaining the best or close to the best results. This reference number 3 and 2 were also models that they also implemented adversarial learning, but instead of using the correlation function, they were using very simple loss functions, like cross-entropy loss functions. For the adversarial component, we showed that the correlation the correlation is basically a better metric. As you can see in all of those models, the fairness metrics, the mutual information and equality of opportunity, our method is basically better than all of the other methods, even those that are already adversarial training and invariant feature learning frameworks. So I was looking at the question. I'll answer the questions after we're done with this part, because some of them are related to what I'm going to talk a little bit later. So this was the model that I showed you was applied to simple like protected variable bias scenarios as I showed you. But in medical applications, we often have a harder task to complete. And that's because, for example, we have two classes of disease and control, right? And as you remember, I talked about it, we do have this correlation between the variables. The confounder itself is correlated with the features, with the input, and also correlated with the labels and the output. If we train this adversarial learning framework, the thing is that because there is this intrinsic correlation between C and Y, it's probably an ill-posed problem, because we want to remove the effects of C from the features, but features are used to predict Y, and Y is already correlated with C. So this is a setting that we can probably find a good solution or a balance between these variables. And this is exactly because, as I showed here, that, for example, if age is the confounder, the two classes already are different with respect to the age. So there is a direct effect between C, the confounder, and also the labels. So in the medical studies, what we often do, so this couldn't be simultaneously true, to predict Y while not predicting C, but C and Y are highly correlated with each other. What we did was, and this is also very much the case in the previous studies, that when we have such settings, what we do is we only remove the confounding effects on, for example, the control group, because we want to remove the effect of age from the measurements, right? And then probably the correct effect of aging is the control group aging, not the disease group aging, because, for example, in some studies, some diseases, like for example, called Alzheimer's disease, we already know that in later ages, the effect of the older ages, the effect of the disease is more seen, is more pronounced. So if we want to remove the effect of regular aging, we should build the model, the confounded prediction model, only on the controls. And that is why what we did was defining this switch here. We defined a switch that would allow us to train the CP module on a Y conditioned cohort. So the condition would be only the ones that are controlled should be able to influence the feature extraction. We denoted this switch by this row. So for example, subjects with a fixed range of like Y are only allowed to affect the features. So in this way, what happens is we learn features with the same like correlation loss functions. F will be mean independent to features will be mean independent to variable C. And that's how we implemented this. It's basically the same loss function that I showed you before, only the this loss component, the second loss, the adversarial loss component, only and only is influenced by Y conditioned cohort, a cohort that is independent from C. Okay, so let me give you an example to understand probably better. Again, going back to the HIV classification problem, we had age being the confounder, features and classes will be our HIV and control. When we run our model, which this work was published in Nature Communications in 2020, when we run our model, again with the differences in age, this is the comparison that you see between the regular convolutional network and our CFNet model, obtaining a much better classification accuracy as well, as you can see here. So we are measuring accuracy on C-independent, or we call it Y-dependent sorry. Let's do this is about the evaluation. If I measure the accuracy on a C-independent subset, that meaning we take a bucket of ages from the two groups, and then we do this on the subset of matched subjects with respect to the confounder, we see even a wider gap between the classes. And while our results are not changing much, the baseline model is actually reducing accuracies, getting worse accuracies, meaning that this age effect is highly pronounced in the model. We also looked at examined whether the predictive power varies across different validation subsets. Like, for example, if we take younger or older patients, what would happen? And we see that in both cases, the models are significantly different, while the difference is more on the younger cases. And this is probably because you see that generally the HIVs are a slightly younger from the control population. So again, this was one of the questions that was asked previously. This is one way of seeing if the confounding variables are actually affected significantly or not by doing further post hoc analysis, looking at subsets, doing correlation analysis, and so on. Same type of like generating interpretation out of the results. We looked at the feature space again in the regular ConfNet. You can see that there's again a pattern with respect to age in the feature space. While our model, there is no bias of the age variable anywhere in that part. And another example is I've shown the young and old subsets. In the young subset, you see that most of the HIVs are actually classified as controlled, which is not desired. So again, we see that the bias effect here, and looking at the impacted regions, same story happens. The ventricles are shown here, while in our model, because the age is removed as an effect, we see that the aging regions are not included in the patterns that we generated. So the classification results, I showed them. I don't want to spend more time on it. We ran experiments on the same data set that I explained to you, the ABCD data set and 6 differences for that. And as you can see here, we also looked at different cohorts and the classification results. In this case, you are actually getting lower classification results compared to ConfNet, and this is very much natural because most of the effects that are coming in terms of sex differences for this experiment are actually coming from the like pubertal differences, pubertal development differences at the age of 9 and 10 years old. So that's basically it confirms our results. And we looked at like different like separate groups as well. If we one of the things that I wanted to actually I should mention here is, if you remember, I was talking about only learning effect on the control group. Here, because it's just about boys and girls, there is no control group to learn an effect of the PDS with respect to the label. This time we ran it separately for boys and girls, keeping them as the like similar to the control group, which improved the results. If we do that Y conditioned training using the row switch, if switch is based on boys or if switch is based on girls, the results are slightly improved while not being confounded by any of the variables. Same experiment was run on detecting bone age from hand x-rays. Again, age was significantly different between boys and girls in this data set in RSNA challenge. We ran experiments and we found out that the models, the prediction models, if we use CFNet, the prediction between boys and girls is actually almost aligned. But if it's if not using CFNet or CFNet without the conditioning part, the row part, you see that there is a difference between the boys and girls in prediction. So this is the bias that we can see in the predictions. So this concludes the second part that I wanted to talk about, and I would be happy to answer questions if there are any.
So there is a question. The first, so I think you have answered the first one. The second question, did you use the same model for the confounder prediction and for the classification models, or two different ones?
So that's a good question. Depending on what the confounding variable is, this model is different. So for classification, it's often like a number of fully connected layers. For the confounder prediction, we also do a number of fully connected layers here, but if this variable is a binary variable, or if it's a continuous variable, or if it's an ordinal variable, this is slightly different in terms of like the task for here for this model. Is it like correlation? Sorry, is it regression type of task? If it's a classification type of task, it depends on each of the experiments. But in general, in terms of architecture, in a very high level, both of them are fully connected layers.
Thank you. So there is another question. If we can predict the bias variables, could we put a zero on, could we basically zero their weights? I'm not sure if I get this question right. So basically, once you predict the bias variables, you can completely remove them and retrain the network. And I guess this is what you're doing, right?
So the thing is, since this is a model that is trained end-to-end, it will try to minimize the effect of confounder on the features. It doesn't say which of the features. I mean, our goal is not to say which of the features are confounded to zero them out. This was the model that we did in the previous, in the interpretation part. Here, we want to learn a feature vector, a full feature vector that doesn't have any effect of the confounder, not to zero them out, because we want the features to be comprehensive and all of them being predictive of Y. But you want to minimize the effects from C. So this is an end-to-end learning framework. We don't zero out anything.
So it's like basically the adversarial part of the learning, which is like similar to the bias-free also feature, the bias-free and also the confounder-free, like the two different parts. Okay, cool. Thank you. Any other questions? If not, then we will continue and then take more questions after you wrap it up.
Yes, thank you.
We still have time, by the way, so we're very relaxed here.
Yeah, since I saw it's 1 hour and a half, I took my time explaining, going to the details of some of the examples. That's wonderful.
Actually, it's good. Yeah, thank you.
Yeah. Okay, the last part, end-to-end learning. We published a paper last year in CVPR. One of my students worked on this, Mandy Lu, which this is the model we call the metadata normalization. I'll talk about it shortly. But in general, we know that in end-to-end learning, forget about the adversarial components now. Say we have a regular network, CNN, ResNet, or even transformer network. You know that there are some normalization models, like for example, batch normalization, there is group normalization and layer normalization, which is mainly used in transformer models. What they do is for each of the features, they correct. So basically, batch normalization and its variants have been extremely successful in improving the training of machine learning models by standardizing features within a batch. However, they do not correct the distribution of the features with respect to external variables. We call them metadata here, which are the same as confounding or bias variables. So these extra variables may create bias or confounding effects. In order to have like a more umbrella term for all of those, we use metadata in this study to basically, we want to correct the feature distribution with respect to the metadata. Back to this diagram that we talked about before, which we basically replaced it with the word metadata as confounders. We call metadata, we define it as shown here. Metadata is data that provides information about other data. And in this setting, we define it as additional variables that are not directly used as model input, but provide information about the input. As we discussed before, I mentioned that metadata and confounders, they do have effect on both input and output. Our goal is to remove the effects of metadata from neural network models. Same story as we had before. Let me do a recap of prior work because it's slightly different in this case because it's a full end-to-end training framework. Prior work and methods which remove impact of protected variables, as we discussed before, include basically generating this using this generalized linear model, a GLM model. It's a common technique for linear models. This technique only works for high-level hand-computed features to build the GLM. It doesn't work on the images directly. Not for pixel level or continuous inputs required by deep computer vision models, machine learning models. Additionally, the prior work, which also performed normalization at the network layers, the network layer level, include batch norm, group norm, and others, which we talked about, but they can't account for multiple or biased distributions. We talked about this as well. And that's why we proposed metadata normalization. Our method is a simple layer that works end-to-end on pixel level data and corrects the distribution shift from metadata. MDN places the regression analysis technique within a network using the key idea that intermediate features of a network may be high-level features. How we implemented this idea in a network, an input layer L with features F, as you see them here, is taken as input to our MDN layer, which this layer projects F onto a space, the metadata space, using the same GLM model. We were talking about GLMs. Now here we want to bring that GLM into high dimensional space within the normalization of features in each of the layers. And then outputs the residual value to the next layer, L to L plus one. So basically we brought the same statistical framework that I explained to you earlier into a normalization framework that we put it in within the deep learning architectures. We know that there is a closed form solution for this problem, and calculating the residual values is not hard. So basically we added this layer and put it in all of the deep learning models. To test this algorithm, what we did was, again, we used several real settings. In the classification of face images, which is a commonly known issue, sensitivity of large pre-trained models to a skin shade, and therefore this is what we did. This was an experiment we provided in this paper. I'm not going to talk about it here very much. The skin shade was our metadata, and we attempted to reduce the dependence of the model to skin shade. Another use case is action recognition, where models may overfit to easier scene cues decreasing generalizability to unseen cases. So this was a video analysis, analyzing the inputs were videos, and we wanted to predict the activities in the videos, but we know that video understanding frameworks are very much biased by scene, because often scene is simpler to capture than the activity and movements in the scene. And we finally use a medical data set. One of the biggest problems in all biomedical models is poor performance when data is taken from multiple sites. So in the diagnosis of neurological disorders from brain imaging MRIs taken from multiple sites, we used the site as the metadata here. Motivated by these important computer vision and medical imaging problems, we demonstrate the effectiveness of MDN in the paper. For the first one, we use a GSPB data set. Second one, there is a huge data set of holistic video understanding that we use as an example for this model, and an in-house multi-site brain imaging data set was used for our case, which I'm going to talk actually about the last part. But before that, we always build a synthetic experiment to show that actually the model is working, the normalization layer is working well. What we did was we created two groups of images randomly with some Gaussians putting there. The ones on the diagonal, main diagonal, they were meant to basically classify the two images. And we created another Gaussian here on the lower left side of the image, which was basically a bias variable itself. The bottom left corner variable was created here. We sampled the data in a way that you can classify them with 100% accuracy if this bias is not controlled for. And if the bias is controlled for, our theoretical accuracy should be something around 83%. Because we created an overlap between the two, like the standard deviation of the Gaussians that we created on the main diagram. Anyways, with that, what we actually did was first looking at the features. As you can see, the baseline model, the features that are generated and the bias variable, there is a correlation, very clean correlation between them. And that's you see the skew there. But when we train the models with the MDN layer on the convolutional layers, we don't see that skew anymore. It's just like the features are not correlated with the metadata anymore. So this experiment was very well showing that we're basically removing the effects of those variables. Also, we looked at correlation variables, correlation values, and on the synthetic data that we generated in different batch sizes, you see that our method is basically the MDM method is basically creating a correlation of close to zero for all of these cases in all of the iterations of training, which means, again, we are not learning any effect of the bias here, while the baseline models are simply just increasing correlation as they train. So basically they are cheating on the variable that they shouldn't be cheating. These significant synthetic experiments are always very good for checking these effects on the data. Back to this brain imaging experiment, we used data from different studies, one from Adni data set, a popular public data set, which we took the control and MCI population, the mild cognitive impairment population. We had a lab data, which we used the control and HIV subjects in that population. And we had a data set coming from the UCSF, a group in UCSF that had a combination of all four classes that we were interested in. So this was a multi-label classification in control, HIV, MCI, the mild cognitive impairment, and hand class, which is HIV-assisted neurodegeneration, which is a combination. It could be counted as a combination of HIV and MCI. So this multi-label classification was performed with the same model that I just explained to you. And as you can see, our model can generate comparable accuracies compared to other methods, while having the minimum correlation between the variables, between the confounders and the features. And we use this D-core, which is the squared distance correlation between the features and the confounding variable, the site variable. As you can see, we are minimizing the correlation while having a more stable, as you can see, the standard deviations is way more stable than other methods that use group normalization, batch normalization, or even the baseline models. We also looked at the learned feature spaces. If we define the three classes, ADNI, SRI, and UCSF, the three different data sites. Again, in the feature space, if you look for one of the testing sets that we examined, there is a clear pattern between the sites, while again, our model was able to basically what we call harmonize the data without the need for any further effort. It was just a linear normalization layer that we plugged into the network. So this is the result from this experiment. One of the important things that I showed right now was we defined this normalization layer. We showed there is a closed form solution to this. And the closed form solution was like this, right? That we have F, we want to residualize, we learn this linear mapping function, and then the closed form solution is just like a very simple list of squares implementation. If you look into solving list squares, you see how the coefficients are easily calculated. But there are several problems with this, several challenges with this formulation. Although it worked very well in our publication in CVPR, but there are some problems, some challenges with it. Instability when using small batch sizes, because we want to create this better estimate in each of the batches, we need to have large batch sizes to be able to estimate better in a closed form solution. So batch size becomes very important, leading to increased training time due to calculation of the closed form solution in every iteration, different results in training and inference, incapability of using the MDN operation for online training, because again, it's a batch level operation. And in online training, it's a little bit challenging. Finally, it's not usable for recurrent neural networks or some of the newer transformer models that they parallelize operations, and therefore it's not easy to implement these batch level operations. What we did in the next work, which is currently under review, hopefully it will get accepted, soon, was basically moving this operation instead of from a closed form solution, move it to the the component, the overall layer overall objective of the network, and define it as a metadata, as a penalty term. So we basically define a penalty term added to the loss function of the entire network. So we showed here that with MDN, the green one, we showed that we already showed that we can remove the correlations, right? We can minimize the correlations, but it works well on large batch sizes. On a small batch sizes, it often doesn't work as well because it can't estimate the effect of the bias properly. With this new formulation, which we called it PMDN, the penalty approach for MDN, even on the small batch sizes, we are able to generate same results. If we look at the same experiment that I did earlier, the multi-site brain imaging experiment, same story with a smaller batch sizes, we are still getting the best results and the minimum amount of correlation with any of the confounding variables. Here we use multiple variables because we put all of them in the multivariate GLM model that we have, and we are minimizing the correlation with almost all of them. This summarizes this last part that I talked about, but before I continue, I think it's not a bad idea to answer the question here, which is how to calculate M. We don't calculate M. The metadata is basically the confounding variables, right? And the confounding variables are actually the ones that are coming with the data set. For example, in this case, the metadata variables are, age, gender, and site. So they are part of the data set coming with the brain images. We already know these variables.
They are prior data, basically predefined, right? Prior
yes,
data.
Exactly.
So, yeah, okay.
Thank you. Yeah, let me conclude the presentation, and then we still have time. If there's any question, I will be happy to answer. So I talked about different frameworks for accounting for confounders and bias, either interpreting their effect or learning features independent from those, and also with a number of ways to do end-to-end optimization for this purpose. At the end, I'd like to thank all my amazing collaborators, mainly at the Stanford and the School of Medicine and School of Engineering in Computer Science. And I would like to thank you who listened to my presentation and these institutes that support my research. And
thank you so much. Thank you so much for this great and very inspiring talk. I mean, you covered a whole lot there. I mean, this is a very challenging topic that was kind of, that was under the rug. Like we were just using machine learning and deep learning models in a very, I would say, in a biased manner, definitely. So confounded too. So there was a question from the audience here. So are dimensionality reduction techniques useful to remove confounders? So like, for example, low rank regularization, like can we, for example, use, I know it's a bit of what you have talked about, but using the concept of low rank regularization, would it be possible to kind of identify those biases or confounders somehow?
That's an interesting question. The using low rank metrics, low rank techniques, or generally dimensionality reduction techniques, what happens is all of these dimensionality reduction techniques, they reduce the dimensionality of the data, but they want to preserve as much as information possible, as many like conclusions you want to make out of the data. They want to preserve all of the effects. So by themselves, these techniques are not very much the same level of bias that you will have in the input. Probably you will see it in the lower dimensional space. However, there are some methods, like for example, one of the methods that could be useful that is counted as dimensionality reduction could be like the canonical correlation analysis, CCA. The thing is with CCA, you're calculating the correlation, you're estimating the correlation between two set of variables. If we say the confounders are one side, the data we have is on the other side, you're calculating the correlation with them, between them. Now you can use CCA to reduce this correlation, to remove this correlation. Although it's a low dimensional like data dimensionality reduction method, but it could be used for the sake of removing or understanding the biases. Other than that, I'm not sure how low rank methods could be relevant unless we incorporate the bias variables, the confounding variables again in them. Yeah, anyways, I haven't seen many papers on this topic other than the ideas related to CCA, which is again related to correlation.
Thank you. I guess this is a new research direction that we probably could explore, right? So I do have a question here in terms of, I was very intrigued when I saw that you have replaced a beautiful mathematical closed form solution with a learning-driven, approach. So my question to you is a bit more like not philosophical, but usually when you have a closed form solution as a mathematician, as an engineer, we're very happy because we can calculate it, we can find it. I know that there are lots of, you talked about computational load, high cost, etc. But what are the pros and cons to making everything learnable as opposed to using ready-made closed form solutions in general?
Yes, I agree with you. This closed form solution was the fancy version of this regularization framework. The major challenge that we had here, as I mentioned, the closed form solutions are good if you have enough representative data to estimate these coefficients. If the batch size, for example, especially in the case of MRIs, because they are 3D data points, data structures, then we have to use a smaller batch sizes because the data itself is large. And then this is a challenge, a serious challenge, especially in MRI analysis, that we can't use very large batch sizes. And if we can't use very large batch sizes, basically this closed form solution, whatever you get here, it's inaccurate. Although it's nice and fancy, but it's inaccurate. In order to make it more accurate, we should increase the batch size, and that's often a challenge with like
small data sets,
data. Yes. And then that is why we moved the same beta calculation of beta coefficients to a penalty in the overall objective of the network. This was the main problem. Another thing is that batch level operations are good, very nice to incorporate in many models, but as I said, like in recurrence networks or in transformer-based models, newer models, these batch level operations they basically if we want to implement them, we will be slowing the networks significantly. And then because these have many parallelized computations, and if we want to calculate everything over one batch, then we can't parallelize anything. And then that's why they will become unusable. In order to make this available and readily usable for other like newer architectures, we propose this new model. One other important aspect that I should maybe mention, we can also go to check out the paper, is we actually solved this problem, although in a learning-based framework, but in an alternating optimization framework, so that it's not just a simple regularization, but the methods implemented are also basically incorporating the same closed form solution in the learning framework. It's not this simple that I showed here. I just wanted to keep it very simple for people to understand the concept, but how it is implemented, again, similar type of like more of alternating optimization frameworks are used and implemented.
Thank you for clarifying. Great. So do we have any other questions? Oh, there is a question about doesn't CCA enhance the correlation? So you mentioned, oh yeah.
Yes. Yeah, so your CCA gives you the highest correlation that exists in the data. So in the two like sides, say the confounders and the features, let's say, if there is a correlation, it will give you the highest correlation possible that you can find between these two sets of data. I said you can use CCA to remove this value of the highest correlation. You can create some feedbacks from the CCA part to the network so that the features that are learned, you get like smaller values of correlation.
So basically you maximize the correlation and then remove those correlations to remove the confounders.
Yes, you penalize the network so that it doesn't give you that high value of correlation.
Great, that makes sense. So do we have any other questions? Let me check. Okay, so that was the last question. I do have one last question just to wrap up the talk. So what about reproducibility? Like I know, like for example, if you discover particular confounders or you remove them in one of these works, did you look at the reproducibility against different training and testing set perturbations when you perturb the distribution of the training set and the testing set? For example, by simply changing the cross-validation, like if you move from a 5-fold to a 10-fold, will you always find the same biases, the same confounders? How do you how do you evaluate the reproducibility of those, basically? Because reproducibility is a big issue in machine learning and deep learning in general. Yeah.
Yes. So I should probably clarify that the confounders, the biases, are often discovered before we build the models. Like as I was showing, like in most of the examples that I showed, we often check the cohorts of the study, for example, and see there is a bias with respect to this variable. Like, for example, I showed in the HIV study, there was a significant correlation with respect to age. In the ABCD study, I showed that like there was a significant correlation. You see, this is the p-value of the correlation is too small. Like, for example, for the HIV study, we also showed the same thing. So basically, these are discovered based on the data and what we have.
Prior data, basically. Got it.
So then what we want to do is, we know that there are these biases. We should design the method, implement the method in a way that removes those effects. And you're right, we often do, when we evaluate, we often run 5 different runs of although all of them are 5-fold cross validation, but different runs with different splits to generate the statistics. These are mainly the mean and standard deviation. I think for this experiment, we ran 5 different runs. And these are just the means of the 5 different runs. But in general, yes, that's the case. With respect to the MDN operation, actually, it's more robust. This one was the most robust thing that we have tested on many different settings, and this was very easy for. That's one of the main reasons that we ran this first on synthetic data was exactly same, because we were able to run this many times on the synthetic data. And again, these I think this diagram is on one run, but the one that we presented in the paper, we showed them in 10 different runs that, and in all cases, it does lead to a correlation of 0. I agree with you that reproducibility is an important factor, but with respect to the confounders themselves, they are determined before building the model. This actually is probably a good segue to also mention that one of the very good future research directions in this field is how to automatically or better identify unknown confounders.
I was going to ask that question. You just beat me to it. Yeah, like the unknown without any prior free. How can you discover them? Any insights into that?
Yes, there are several studies. We haven't done anything now, but there are several studies based on causal learning, for example, that you can identify the confounding effects of the variables and create like that causal graph, and based on those identify the confounding effects. But yes, I mean, it's a research field. There are several many papers right now coming out of machine learning conferences in this space, and it's a great future direction for medical applications too.
Wonderful. I can't agree more. Thank you so much for the talk today and for answering all of our questions. And I guess many of the attendees here, I think many of them are being exposed to this wonderful topic for the first time, which is really exciting. And thank you, Ehsan, for joining us, for your talk, for the great work, and hopefully we'll get to see you soon in Singapore, probably. We'll see that.
Absolutely, yes. Thank you. It was great talking to you and being here.